Hey, hi folks. Thanks for joining in today. My name is Arun. I'm here to talk about Bazel for Android development. So before we begin, bit of introduction about me. So I'm an Android engineer at Grab. So Grab is a super app. We primarily serve the Southeast Asian market. So we have several different services like transport, payments, food, etc. There I work primarily on developer experience, build systems, infra, CI/CD, app architecture, and stuff like that. So before Grab, previously I used to work with Freshworks and Bytemark, both in the consumer and uh, business domains. Previously, I also worked as an independent Android developer publishing apps on the Play Store. So I'm here today to talk about Bazel. So much of this agenda today will be focused on, okay, I'm an Android Gradle based engineer today. So what does it take for you to start trying out Bazel, and what are the things that we should know? So there will be a lot of comparison between Gradle and Bazel and how to interact with both of these build systems. And then we'll talk about the state of Android support. So where the Android support is today and what are the trade-offs that we might need to make. And then finally move on to a couple of interesting bits like Bazel performance. Then we talk about migrating to Bazel. If you if you're interested in that, the steps that you could take, as well as how Grab's own tooling can help here. Then we finally talk about advanced Bazel, where if you have a large project, what are the couple of at-scale features that you can use from Bazel, and then we move on to the conclusion. So let's begin with answering the question, what is Bazel? So Bazel is an open source build system from Google, and it is based on Google's own internal build system called Blaze. So Blaze is used to build the infamously the Google's monorepo, which is known to be several thousand modules in size, and they needed a build system built for building such a large repository. So it was built from the ground up to be multi-language and multi-platform compatible. It makes sense because in a large monorepo, it is often the case that you work with different languages and different stacks across the team, and it is always beneficial to have a build system that is compatible with all of these situations. Now, from the ground up, Bazel was built to be highly parallelized, and it is really interesting on it that the Bazel system was designed to be parallel, and it can even do distributed builds where your build is not restricted to your own laptop, but rather it can be distributed to servers on the cloud, for example. And it is known to be performant on large code bases. So it is really a vague claim to make. I would like to go in detail on what this means and what are the trade-offs that Bazel has made that allows it to be performant on large code bases. So first, let's begin by discussing the Gradle and Bazel build configuration. I strongly believe build configuration is one of the key areas that is different between both of these systems that allows this build system to scale in their own ways. And let's start with Gradle. So in Gradle, this is how a typical build system might look like. You might have plugins, you might have an extension to configure that plugin. Here I have Android extension block and any other statements that follow it. It is one of the interesting bits here is this last line statement called println, where I'm trying to print the current time milliseconds at the time of evaluation. Now, I as an user, the correctness for me is that this line should always evaluate and print the time at that time where the build script was evaluated, and it would work just like that, like when you run configuration on this build. But let's talk from a build system point of view. As and when I added this statement, it becomes really hard for the build system to know when this file is up to date. Meaning, I cannot safely skip evaluating this file without breaking correctness. So if I skip evaluating this file, I cannot no longer print. And at the same time, if I start printing this uh, time milliseconds now, imagine scaling this build configuration to thousands and thousands of Gradle files. All of this has to execute again and again. Basically, they become non-cacheable. Now, this is where all of these things are done in the configuration phase with Gradle, and at the moment they are single threaded. Why? Because it becomes very difficult to track build or Gradle dependencies, just because that you cannot safely say, okay, at this point in time, the build or Gradle is up to date. I don't need to evaluate again because build or Gradle, the programming environment there is very mature. That means you can use rich Java APIs there. The up-to-date check of the build.gradle file might be dependent on the code, which cannot be safely evaluated without running through code through a proper JVM runtime. Now, even though this is a known problem, this is being addressed by Gradle. So we have configuration cache, which helps reduce the incremental build time, mainly by caching the results. So even though the println statement might evaluate the first time, from the second time onwards, we sacrifice a bit of correctness. We skip evaluating it again, and we cache all the results so that we can save evaluating the files again. So with configuration cache, your build starts instantly because it is able to uh, cache results from previous build. And another thing is that it is able to execute the tasks in parallel. Previously, we know that there has been a lot of push recently in the Android community to modularize, and I quite agree with it. Mainly because when you modularize, independent tasks run in parallel, and as well as even though independent tasks run in parallel, tasks in the same project still run serially. But when you use configuration cache, you have parallel. So we talked about Gradle. Now let's see what Bazel does here. So Bazel uses a dedicated build configuration language, and it is named Starlark. So I'm quite a bit fan of Kotlin. So I like the type safety, I like the expressiveness of the language, and I've built quite a few DSS myself. But having worked with most of these in the past few years, I still believe Starlark is better suited as a configuration language, and let's see why. So it is very simple and it is quite small. It does not have a huge API surface and it carries the Python dialect at the moment. So if you know to read Python code, you can get started with Starlark straight away. And it was designed from the ground up to be tooling friendly, meaning you can have all the Bazel build script being manipulated by scripts, or you can even generate them. And this was done consciously done because there is a lot of benefits to doing that. Let's find out later on in the presentation. And because it has very limited APIs available to them, the up-to-date check is naturally derivable in Starlark. And because of that, Bazel can do parallel files. And it has something called hermetic execution, which is really interesting because hermetic execution basically means that you don't have access to the file system network or any system clock or any other thing that could make your build file not up to date. Just like we saw in the example where I was printing the time, that is no longer possible in Starlark because Starlark code is very strict and you can only have limited set of things to do. But this contradicts what a build system is supposed to do. What is a build system if it can't access the file system? You can definitely access the file system, but not in the configuration phase. That is how Bazel is able to be quite a bit faster in the configuration phase because it disallows many of the things the that would risk the correctness. So here is a sample code, and it is very easy to mistake it for Python because the syntax is exactly the same. Now, couple of characteristics of Starlark are that the build files are evaluated in parallel because the each build style has a load statement, and the load statement can infer a allow Bazel to do dependency analysis. And once you have this build file evaluated, the state is cacheable. So that means if I have thousands and thousands of Starlark based build or Bazel file, if I make one change to one of them, only that file will be evaluated for incremental build because Bazel knows that rest of the build or Bazel file did not change. It is safe to skip evaluating them. Now it carries build or Bazel and BZL extension. There is only a slight difference between both of them. Build or Bazel is typically completely declarative. You can't have, let's say, a for loop or something like that. It is only for declaring um, build rules and then consuming them. But BZL can be used to declare new types or new functions to the build or Bazel environment. Here is a simple example for a load statement. So I can simply, the load sample is quite simple to parse from many parsers. You can simply say that the merge R classes is coming from utils.bazel. Now, ha- now we saw basics of build configuration between Gradle and Bazel. Now I'll try to draw comparison between what uh, workspace and settings.gradle is and how closely are they related. Settings.gradle is where you typically have common plugin blocks. You maybe we include a lot of modules there, and then we add a couple of settings plugin and configure build at the root. The closest thing concept that we have in Bazel is workspace. So workspace is where you bring things into your build. So when you create a fresh Bazel repository, it does not have anything. It does not even have basic way to do a copy file or something like that. It has to be either ma- imported or it has to be either written custom. So the way to fetch dependencies of your project is done in the workspace file. And here are simple function calls. It exactly looks like a function. Git repository is a function. HTTP archive is a function, which basically says that clone this Git repository and make it available as a dependency. And at the same time, the second one says that fetch this HTTP archive, unzip it, and inside it you will find a Bazel repository. So these are nice abstractions, and most of the Bazel community uses this way. And it is quite common to have Git repository tracking, and as long as you provide the commit and SHA sum, we'll be able to compile that. And one other thing that is different here is that in settings.gradle, it is common to include all the projects that your modules your project may contain, but that is not needed in Bazel, where the targets are automatically discovered. And workspace is where you configure your SDK rules toolchains. For example, if you have a dependency on a Java toolchain, workspace is the place to do it. Now, how do I fetch external dependencies, right? So a common pattern in Android-based Gradle builds is that, okay, you add an implementation on a Maven dependency, and Gradle is smart enough to do a lot of smart things like dependency resolution, and give you this artifact for compilation, your for your app at runtime. Similarly, the way that we do it in Bazel is that again via workspace. Workspace is a bit more lenient, and it is lenient because of repository rules. We'll discuss more about repository rules later, but it is at the moment it is important to note that the Maven artifacts are provided by a separate tool called Maven Rules JVM External, and this is a syntax for consuming artifacts hosted remotely from a Maven repository. Now, I touch based on a concept called rules. So in Bazel plugins, so both Gradle and Bazel took different approaches to extending each of the build system. So on Gradle, we know that we have Gradle plugins. So we have Gradle plugins for various things, and Gradle plugin is typically used to extend the build. And for example, there was Android Gradle plugin, and then it was extended with Kotlin Gradle plugin or Android extension, stuff like that. So this is primarily done by mutating on a mutable project or setting system. So if you're writing a Gradle plugin today, you are given a project instance or a settings instance, and it is typically mutable, and you're adding on top of this, and you're configuring the build, and depending on whatever you want to do, maybe register a few tasks in the process. But this is an interesting problem again, because since this is a shared global mutable state, multiple plugins, there is a chance to compete on configuring few things. And in my own experience, this is quite a bit common. Like if you want to configure Java options, and what if another plugin has already configured it, there are cases like this. And nothing is solvable without a simple after evaluate block. But again, I'm just kidding it blocks, because your plugin interoperates purely with the rest of the ecosystem, because it assumes that no one else would configure again before the after evaluate block. So how does things work in Bazel? So in Bazel, it is done by a concept called rules. So rules basically are single isolated units of units of type units where you have certain actions composing producing several artifacts. So as an example, we can have a C++ rule that can build a C binary, and you can have a Java rule that builds Java jar file or something like that. Now, let's say I want to build an Android library that can compile NDK code as well as obviously compile Java code. What we do is that we in Bazel we call this rule-based target composition, where you compose new rules based by using existing rules. So in this case, I typically write an Android rule that delegates C++ compilation to C++ rule and Java compilation to Java rule, and it so similarly, this can be extended to Kotlin. So the Kotlin rule simply calls into the existing rules API. So you have a well-defined structure where the rule can decide to expose few things to you, certain APIs, and it can also decide to hide few things to you. So this is how uh, we add capabilities to Bazel. So we have different rules for Kubernetes, Golang, Kotlin, Android, stuff like that. So we saw about rules and plugins. So with that knowledge, let's try to see how a typical build.bazel file would look like. So this is the typical build.gradle file. We know that we apply the Android application plugin, we configure the Android extension block, and then probably min SDK, version name, flavors, and stuff like that. And then we configure the dependencies. The equivalent script in Bazel would look like this. So on a high level, it is simply a function call. So Android binary is a rule here, and it simply happens to have a lot of named function arguments, like name, custom package, manifest values, and stuff like that. One of the main differences both of these two are that on the Android binary side with build.bazel, it is quite strict in the sense that there is no imperative code allowed. You cannot have simply have an if-else statement configured dynamically, because doing so breaks Bazel's guarantees that it provides during the configuration phase. So Bazel is very strict about saving its configuration phase performance, so it does not allow you to be dynamic in your expression with build.bazel. So that means it is not to say that complicated things are not possible in Bazel, because you can always use rule-based target composition to extend further. For example, if I want to post-process the APK after Android binary generated, I simply wrap it in a new rule that delegates the work to Android binary and does its own stuff. Now, let's talk a bit more about project layout. So this is a typical project layout that we have in Gradle. We have multiple different modules. I have Android binary, I have an Android library and Kotlin here. And build.gradle mirrors it is the first file in the project layout here. And it basically says that, okay, this is a Gradle module. Now, how does it look like in Bazel? So in Bazel, you typically have workspace and build.bazel file for each of these modules. Now, this is where it gets interesting in the sense that Bazel goes a bit further in breakability of targets. Meaning, so if I have a sample Android module like this, and as I already said, I have a build.bazel file mirroring build.gradle file. Now, Bazel allows the opportunity to break the single target further into multiple nodes by allowing you to have build.bazel for each packages as well. And this is one of the trade-off that Bazel makes for performance. Why? Because Bazel's configuration phase and all of these systems are really stable in the sense that as long as you break your build, or you break your you make sure that your build graph is wide enough or such that Bazel is able to execute them in a parallel fashion, and also it takes care of caching and stuff like that. So what this means is that breaking down targets is encouraged in Bazel, and that means a single build.bazel file can potentially contain multiple targets. And this is the official recommended approach. And at the same time, while you have a lot of performance, because you have imagine your only way to speed up in Gradle would be to break this big module into a build.gradle file and then pay for the added configuration time as well as a bit of cognitive load because the module is split. Whereas in Bazel, you retain the same structure. You worry only about breaking the models based on your business use case rather than the build use case. Once you break down the project based on your business use case, for optimizing the build, you can always break the big module or the isolated unit of the module into further smaller bits by adding more build.bazel file and compiling them. But again, the trade-off that we get here is that the build script is verbose now, because instead of meeting a single build.gradle file, you potentially have to maintain a lot of build.bazel files. A couple of other things compared with Gradle is that we have Basilisk. Basilisk is the equivalent of Gradle wrapper that we have. So it basically allows you to download any version of Bazel and then compile with that. So you don't rely on system installed Bazel version, which is really important because when you have a large team, it is important that everybody stays in. And then we have Gradle properties, which is similar. We have Bazel RC, which is similar to Gradle properties. So it is common in Android Gradle plugin or even Gradle to specify a couple of build properties in Gradle.properties file, and that those are mostly experimental flags. For example, non-transitive R class or a couple of flags for enabling incremental annotation processes. Now, one thing that I like about Bazel is that it has explicit definition for a local property. So you can optionally add a local bazel.rc file and not check in that file so that it applies only to you. On Gradle, it is sort of agreed upon that for at least for Android builds, you have a local.properties file, but the priority is still not clear. So it is possible that the different teams or different projects consider the priority of local.properties a bit differently. On Bazel, it is more explicit because in Bazel.rc file, you are in control of where you define, like you can always say that my local property overrides whatever is present on the master or main branch. So what about terminologies that is very distinct between both of the build system is modules versus targets. So as I already mentioned, Bazel considers each build or Bazel file a rule. The outcome is a target. So if I have two Android binary definitions in a build.bazel file, that means I have two targets inside a package. And Gradle's approach here is completely different. For a single build.gradle file, you don't typically create you don't apply the plugin, Android application plugin twice. You only apply it once. And if you want to apply it twice, you have to either move it to a different directory. So ultimately, you have single build.bazel file and you can keep on breaking down into multiple targets as and when it fits your needs. And one other interesting thing is that Bazel is not task based. It is an artifact based build system. And this is again a deeper topic for us to discuss. But then again, to put it in simpler terms, Bazel does not operate based on tasks, whereas Gradle is task based. Meaning, in Gradle, I can simply say that, okay, do assemble debug, which means that run the assemble debug task specifically and produce the output. But on Bazel side, it is artifact based, meaning it always works in terms of file outputs. It does not have a concept of executing a particular action. So if you want an APK file from Bazel, you explicitly ask to build that file. You don't typically say, okay, run this action that would give me this file, but rather you ask for the file and it leaves Bazel to figure out how to get that file for you. It can fetch the local disk cache, it can fetch remote disk cache, and it can fetch anywhere to get that file for us. So targets in Bazel are referenced by their label. So this is a simple label that we have, like sample slash app and app.apk. What this basically means is that the first bit, the slash slash, is called the repository. So in Bazel, it is common to have different repositories. Everything that we define in workspace are mostly external repository. For example, I might be downloading Dagger. The Dagger jar file might come from an external repository and it might be tagged at Maven. But the sample target that I have in the slides here is coming from my own project sources. So it starts with double slashes, and this is the package. So every path, every path that follows the slash is a package. And finally, we have reached the target. And at the end, we have app.apk, which is the file that we want Bazel to build. I mentioned about task-based and artifact-based. A recommended reading here is from Software Engineering at Google Book, where they discuss about the build systems and build philosophy and why they moved to an artifact-based build system like Bazel. So, what is the state of Android support in Bazel? So, we talked about build configuration, how to configure builds between Gradle and Bazel, and how the configuration languages differ. So with that said, what does it take for you to start using Android rules in a couple of sample projects, for example? So we know that we have three different major projects contributing to our everyday builds, which is the Gradle project itself, which is a completely independent project. Then we have Android Gradle plugin, which uses and then we also have the Kotlin Gradle plugin, which sets up the Android Gradle plugin for Kotlin compilation. Now, similarly, on Bazel, we have the Bazel binary. So when you build Bazel from source, you get a Bazel binary. Unfortunately, due to various early implementation where there were no good separation of concern at the moment, currently, Android rules, C++, and Java rules are built within Bazel. So the Bazel binary that we have not only includes capabilities of like the artifact-based performance or Starlark compilers, it also have capabilities of building Android, C++, and Java. While this is well and good, it poses two challenges. Mainly, it it means that it is very difficult to fix a bug in Android because it might be closely tied with the version of Bazel. And at the same time, fixing any bug in Android rules, meaning updating the Bazel binary altogether. And this is a known problem. However, Rules Kotlin is a different project. So we have a separate release cycle for Rules Kotlin. So we know that this is going to change. So we have focused effort to move it in a such a way that we have Bazel binary and then we have a collection of rules that would simply use the Bazel like how we have in Gradle. So this is the long-term approach that we have. So currently, native Android rules are being migrated into their Starlark versions. Native Android rules are written in Java inside Bazel binary, and then we have Rules Android project. However, it is not stable yet, so there is still a migration going on in the pre-alpha branch. And as of today, while the migration is going on, the recommended stack for Android support is still use the native Android C++ Java rules alongside rules Kotlin, which is again a different project. Now, we talked about a couple of good things with Bazel and performance, like how is Kotlin compatibility today? There are few features that are not exactly supported by rules Kotlin. So one such feature is data binding or view binding. So even though there is official support for Java, Kotlin support is bit lagging, especially when you use binding adapters or couple of complex data bindings. We have managed to provide support for this by Grab's own rules, which backport some of this functionality so that current Gradle projects using data binding can be successfully built with these rules. But this is not an official solution. And at the same time, Kotlin's Android library rules, the resource processing bit not optimized at the moment because it is waiting on the Starlark migration of Android rules. So once we have the rules Android project maturing, we'll be able to, the Kotlin Android library rule may be able to use the Starlark versions of the API. Again, this alludes to the previous fact that we have rule-based target composition where each rule can simply use a public API for the other rule to form a new rule, right? So it is waiting on that bit. And there are a couple of advanced performance optimizations in Java plus Bazel that are not directly available in the Kotlin, but there has been good progress. The scaffolding is already done, And this mainly involves around reducing the number of targets that rebuild when you make a change. So let's talk about performance. So Bazel is artifact based, we already mentioned. So basically, you can consider it as transforming one artifact to another. And in pure functional terms, we can simply define it as a pure function in Kotlin, simply saying that there is an action method that takes an input list of artifacts and transforms it to other. And one could argue this is the same thing that Gradle does, right? So in Gradle also we have the input and output concept where input produces the output. As long as you produce this, you give the same input, you're going to get the same output. But Bazel goes one step further here. It also attaches the tools as part of the input. This is the one stark difference between Gradle and Bazel in the sense that Bazel is so strict in what you do inside your execution, meaning it executes in a very sandboxed area where you don't have access to your system installed tools. So you have to tell Bazel that, okay, I am doing Java C inside my action. So you have to ask Bazel to provide the tool for you, which then Bazel does. The reason it is built this way is because of correctness. So wherever you execute this action, it is always going to be correct because the tools are predefined. And because the tools are forcefully asked to be predefined, Bazel is able to do a couple of cool things like sandboxed execution, which means better cache hit rate. Secondly, it is able to take this abstraction and run it in a persistent process like Gradle daemon. And even it is confidently able to distribute this action into multiple servers there. So, for example, you can actually do a remote build with Bazel where you're not limited by your capabilities of your laptop or your local workstation, but rather distribute the build into a powerful set of clusters where each cluster would perform this action. And this is purely possible because Bazel has the data that it needs to do so, which is input and tools. And at the same time, in order to do this, all the input ahead of time. That means on Gradle, it is common to have a folder where you write a lot of files and that give the files blindly as input to another task. But that is not the case with Bazel. All the inputs needs to be known ahead of time so that Bazel can be very smart in compile avoidance or performance. And zipping outputs is a common approach when you don't know the file names in advance. And at the moment, it does not support file-based incremental build, which is a stark contrast between Gradle and Bazel, where Gradle, much of the investment or even the Android Gradle plugin investment into do incremental builds, but Bazel does not have this concept. You have a large project, a large module, let's say you have 10 Kotlin files, you make one edit to the one Kotlin file, all the 10 file is going to compile again. And it seems strange at first, but let's see how Bazel is able to give performance there. And configuration cache is out of the box with Bazel. You don't need to do anything to enable configuration cache. And most of the build will be, even the first build will be quite fast because of the parallel evaluation of Starlark files. And once it is evaluated, it is quite instant incremental build, and you can entirely skip the configuration phase. And one of the nice things about Bazel is that it already supports EBA-based compile avoidance in Kotlin, which is an experimental feature in Kotlin 1.7, and it's being worked on in Gradle land as well. What this means is that, let's say I have a function called hello, and I have a println method that says print hello world. Now, what the ABA-based compile avoidance means is that Bazel and rules Kotlin combination produces a separate artifact called ABA jar, which means the binary interface, and it does not have the private method bodies at all. So what happens is that when I edit the hello world into, let's say, hello Chicago Roboto or something like that, it does not change the output of hello ABA jar. That means all the dependent modules need not recompile again. And at the same time, this is one way of reducing the scope of your changes. So I going back to the 10 Kotlin file example, I can simply split the target into multiple build.bazel entries, and all of the dependent modules won't recompile as long when I make small changes. And let's say you want to migrate to Bazel, and there are several strategies to go about this migration. Based on our own experience, so we can do either incremental migration, one shot, or hybrid. Incremental is when you gradually migrate few modules to Bazel and then keep both Bazel and Gradle at the same time. Whereas one shot is just sit one weekend, completely might generate all the build.bazel file and then have the build ready. This might not be practical for a large project. And then there is hybrid build. So Graph has its own migration tooling, and which is what we use to migrate a large 3.4 million lines of code project with Gradle to Bazel. And it simply looks like this. It is simply a Gradle plugin, and simply running Gradle migrate to Bazel would read through all the Gradle API information and then generate equivalent build.bazel file. And this is where the tooling compatibility of Starlark really shines, where it is relatively simple to generate Starlark rules because it does not have complex syntax or anything. And once the project is migrated, the entire build can be run with Basilisk and it produces the output APK. So with Grazel, it allows us to keep Gradle as a source of truth, meaning until the migration is done, we still have Gradle as a source of truth. That means it is non-disruptive to feature development. So as and when feature changes, the build.bazel files automatically gets updated and the developers don't have to manually go through these changes. And one of the goals for us too was that make this risk averse in the sense that uh, there should not be any build system induced changes to the code base. So architect in terms both in terms of architecture and performance. And it does one more thing called hybrid builds where it can compile part of the dependency graph with Bazel and then compile the remaining non-migrated ones with Gradle as well. And this is mainly made possible because of Gradle's really flexible configuration phase, which is again the trade-off that we discussed in the beginning. We were able to use the configuration phase to configure build in a such a way that both the build systems can work together. The Grazel is currently open source at Grab Grazel, and we also have supporting rules and macros. So one of the things that we learned early was that establishing build macros early allows us to adapt strategies later. So as and when we were learning a couple of best practices to do Bazel configuration, it made sense to have an abstraction, just like the rule-based target composition that we talked about earlier. So here is an example. I'm simply defining an Android library, but what I'm doing is that inside the body, I'm simply delegating it to the native Android library rule. What this allows me to do is that I'm able to customize the arguments that goes into the Android library. We do have a couple of our own Bazel rules for Android apps, and it has a couple of missing features that Android Gradle plugin provides, but Bazel does not. For example, build config, resource values, and data binding support and stuff like that. Now we are realizing that all of these could be abstracted into a nice one-shot Android library rule where build config can be a simply uh, a method argument instead of a separate target. But again, that is how we learn. So there are advanced Bazel concepts as well, depending on your team's needs and capabilities, which is remote caching. So Bazel is able to it's quite sensitive to caching. We already discussed that the surface area that Bazel touches for generating the cache key is quite huge in the sense that it snapshots both the files and the tools to build the cache. That means as long as you're building on the same system, you're gonna get consistently higher number of cache hits. But then again, if you're running on a slight change into tooling, it is possible that you'll be missing caches. In our own experience, it was relatively easy to achieve like 99 to 100% caching. But one of the limitations that Bazel has at the moment is that you cannot share caches between Mac and Linux because the operating system path is different. But this is a known issue and it is being worked on in some capacity in the Bazel repo. There is also remote execution. You can use powerful servers on the cloud to distribute your build. For example, in our own experience, we were able to use parallelize the build up to 200 threads simply by using. There are a couple of open source projects that already implement this protocol. One such thing is Bazel Build Farm, which is from the Uber team. There is also queries. Queries allows you to. There are there has been a lot of Gradle plugins which tries to answer the question. Okay, where is some dependency coming from? Who's using this? What are the artifacts that are being produced? Because Bazel is able to operate on the Starlark files more easily. It is able to provide this feature called the Bazel query, and it allows us to answer these questions. And it can also draw diagrams into your project build graph, and this is a first party tool. So coming to the summary now, so the Bazel excels in scaling build configuration. So you can have thousands and thousands of build out Bazel file. It is going to evaluate very quickly, and it is going to cache all of them, and it is going to evaluate them parallelly as well. And at the same time, when you have a very large project, you can utilize features like remote caching and remote execution. So remote execution, especially, it is basically throwing more muscle at the problem. And for large projects, it can be helpful. There's an upfront investment cost. So at the moment, Android Gradle plugin direction and Bazel rule direction is a bit different. So if you have a large project and if you're deciding to migrate, then there is an upfront investment and to do a bridge solution first. For example, it might be build config fields or supporting data binding or resource values or something like that. Yeah, and it often makes sense to have a dedicated group of engineers that is able to build this missing features so as to keep up with the migration. And at the same time, because the tools and build configuration are very easy to manipulate, if you do an automated migration like GRAZEL does, it is mitigates the risk of maintaining two build system. In our own case, however, we were able to keep Gradle as a source of truth and simply put the migration on an autopilot mode where we were able to work on different other things like caching and other things without touching the project. And at the same time, since we have automated migration, at the moment, Grazel does not support per package targets, which is important for Bazel performance. But this is an area that we are really interested to try to basically look at a Kotlin module or a Android module and automatically generate multiple build-out Bazel files based on the code structure. So this would help to parallelize build targets even further and reduce the burden of maintaining a lot of build scripts. That's all, folks. Thanks a lot for joining in today. And once again, I would like to thank John and Victoria and the organizing team for giving me an opportunity to present here. Thanks again. Um, so there are a few questions in Slack. So one of the question is, can you run Bazel in most of the OSs, Windows, Mac, OS, and Linux? So although okay, I'm sorry. I think I'll continue. So it is technically supported, but in our own experience, we have been focusing mainly on macOS and Linux. In the beginning, Bazel does have a close ties with Bash-based tools, so it tends to have a bit of dependency on Bash tools like CP or something. Is not as abstracted like Gradle is. So there is a bit of alignment into Mac OS plus Linux, but officially there are Android rules. Officially, the Android rules does have test cases for running on Windows. There was another question from Ryan. Do you give up flexibility by having many rules built into the Bazel binary getting in the way of working around missing features of bugs? So yeah, so as I already said, having rules built inside the Bazel binary is a bit of pain at the moment in the sense that it makes it difficult for Android to independently of Bazel releases. But at the same time, for missing features and bugs, at least what we did was to have a separate project called App Bazel Common and basically wrap this native rules inside our own macros. So our macros API provides a sort of an boundary between the native rules and uh, the official native rules and what the project will be seeing. So what this allows us to do is that even when the native rules support gets updated or the API changes, we are able to fix it by simply changing the macro implementation instead of changing the entire build script on such. Again, the rules on Android, at least in Android in particular, the migration is ongoing. There is no defined timeline yet, but once all the native rules like Java, C++, and Android are moved out of Bazel, I think the ecosystem will be much better. That question: is it possible to migrate a large project to Bazel incrementally? So I like to call attention to Grazel's hybrid build feature. So one of the goals that we have in Grab was that we have quite a large project. At the time of migration, we were around 1,000 modules, and we have grown even further to 1,500 range at the moment. So Grazel allowed us to do incremental migration simply by doing hybrid builds. So it can look at a project and determine whether it can migrate a module successfully or not. All the modules that don't pass the migration criteria gets filtered out and basically extracts a subgraph, and only that subgraph will be migrated. So what this allows us to do is that we keep on adding more features to your custom rules, and once your custom rules matches the 100% feature parity with Gradle, then Grazel would be able to build a binary for you. But until then, you can do an incremental migration. So the way that we did was that we even had a dashboard to track the number of modules that was migrated, and then it makes sense to dependency graph changes as and when feature development happens. So a module that is migratable today might not be migratable tomorrow because the dependency graph changed. And having an automatically regenerate the scripts made it easy for us to keep the main branch always green with regards to Bazel.